All right. Yeah, so today we'll be looking at electrolysis, and we're looking at electrolytic cells as compared to galvanic cells. So we started off with galvanic cells a while ago, and the simplest or most common galvanic cell that we saw, right? We had our copper solid, right? We had copper solid was our electrode, generating copper 2+ ions, which are aqueous. And then so that's our anode, right? So that's our anode half reaction. And in our cathode half reaction, another common cell or common half reaction that we saw was zinc solid, right? And for a zinc solid, we had zinc 2+ aqueous aqueous ions. Right, so with copper and copper 2+, this is a 2-electron process. So we're saying that we have 2 electrons being transferred, right, from anode to cathode, a 2-electron process. And then finally, we put all of this together with our salt bridge, where we have, in our salt bridge, we want potassium, our positive ion to go to our cathode, our negative ion to go to our anode, and that's because our anode has a positive charge, right? So we want to regenerate negative ions or negative species there from the positive charge. And since our cathode has a negative charge, we want to make sure that we're generating positive ions from our salt bridge there. So in our salt bridge, we should have KCl, which would also be aqueous, and these would be our aqueous species. And this allows us to maintain charge neutrality, right? So you can imagine that our copper and our zinc don't exist as species all unto themselves. We can just pick some general reagent like copper sulfate, right? So if we're starting off with copper sulfate, CuSO4, and then we also want to have zinc sulfate, that would be our ZnSO4. You can imagine that sulfate would be our spectator ion, and for each half reaction, we can say that we have copper solid going to copper 2+, which is aqueous. And then this is a 2-electron process, right? So that's our oxidation half reaction, our anode and oxidation half reaction. For our cathode and reduction half reaction, we'll take our zinc 2+ ions, and since it's reduction, electrons are reactants, and then this allows us to generate zinc solid, right? So this is just a standard galvanic cell that we've looked at. Now we want to switch from looking at a galvanic cell to our electrolytic cell. For our electrolytic cell, we're saying that all of this occurs in one space, right? So before, for our galvanic cell, we had 2 chambers, our anode oxidation half reaction, our cathode reduction half reaction, and these were 2 different chambers. Now for our electrolytic cell, it's all occurring in one chamber. So one example that you may see, or you probably would see, is using lead bromide. So lead Br2, which is a liquid, and this generates lead as a liquid, and and Br2 as a gas, right? So we're applying enough energy for this to happen, and you can imagine that our flow of electrons still occurs from left to right. Our anode is still on the left, so this is still our anode, and this is our cathode, right? Our cathode is still negative, our anode is still positive, right? In this flow. And now what we're saying is that oxidation is occurring at our anode, like before, and reduction is occurring at our cathode. But now we want to think about PbBr2 as a liquid being our solution. So that's this gray area. And we want to think about which ions will be attracted to which electrode, right? So if we're saying that our anode is positive, then our negative ions would be attracted to that electrode, right? So we can put all of our BRs, Br minus, Br minus, Br minus, and Br minus, surrounding our positive electrode. And then our positive ions will surround our negative electrode, our cathode. So now we'll have, I want to use a different color. So now we'll have lead 2 plus, and lead 2 plus, right? And we're saying that in this cell, right, in this electrolytic cell, our bromines will combine to give us Br2 gas. And then our leads will combine to give us Pb as a liquid. Lead is a liquid, right? So if we were to think about the cell potential for this, our E0 cell, we can use our standard reduction potential tables to figure out what this value would be. So reduction occurs at our cathode. So we'll use our lead information, our lead value there. So that's 0.125 volts. And then we need to add our anode half reaction. So that'll be negative, excuse me, 1.065 volts. So our total E cell here would be negative 1.190 volts. And you'll notice that for this E cell, we have an E cell that is negative, which is an indication that we're looking at an electrolytic cell, and it's non-spontaneous. Electrolytic cell, and this will be non-spontaneous because our E cell value is negative, right? So that's basically what we looked at for example A. So all of this is just a representation of example A here.